Hello everybody and welcome to the video on section 6.4. In this video we'll cover two new algorithms, the nearest neighbor and the repetitive nearest neighbor algorithms. These algorithms, like the brute force algorithm from section 6.3, are designed to solve traveling salesman problems. So again, the global setup is you are a salesperson who has to travel to several different cities and then return back home to your city. What's the least cost way that you can do this? It costs to get between any given two cities. So how can you travel through all the different cities and minimize your overall cost of doing so? Now in section 6.3, we covered a method that would solve any traveling salesman problem for you. And the method went like this. You have your salesman graph in front of you. Okay, you have a graph with costs on all of the edges, and you can get from anywhere to anywhere else. If you want to figure out the cheapest route starting and ending at a particular vertex, one thing you can do is just list out all possible routes starting and ending at that vertex, compute all the corresponding costs, and then choose the least cost path among them. Now, as we talked about in the previous video, this is not efficient. It is optimal in the sense that it will give you the best answer, but it's not efficient. It takes forever to do this. And the more vertices you have, you're going to take exponentially longer to solve your problem. So the brute force algorithm from section 6.3, even with the computer, you can only do it with like 21 vertices or something. So if you're just sort of your average FedEx delivery guy who has to make 30 deliveries in a day, section 6.3 won't help you very much. So in section 6.4 and 6.5, we will study some other algorithms that are not optimal, so they don't guarantee you the best answer, but they are efficient in that they are quick to implement. So the nearest neighbor algorithm is a fairly intuitive method for solving a traveling salesman problem. And again, if we were in class, I would ask you, suppose you don't want to write down every possible route. Can you design for me a method for finding a good route? And I want this method to be simple. And generally, the students in class will come up with this algorithm. They won't call it this, but they will come up with this. And basically, the way it works is you start at wherever you're supposed to start. And if for us, there will always be a designated start point, so that's a moot point there. From the starting vertex, go to the nearest neighbor. And by nearest, what they really mean is go to the place that's cheapest. So I'm at city A, and maybe there are 3 other cities to go to, B, C, or D, right? Just go to the one that's cheapest. That's all you do. And once you've gone to the next vertex, go to its cheapest neighbor, making sure that you don't revisit vertices. Okay, so remember that in this setup, once you visited a city, you don't go back. So at any given point in this method, just go to the cheapest place. That's possible, without retracing your steps. And you keep doing this until you close the loop, until you get back to where you started. So just for example here, here's Earth. This is the example from section 6.1 and 6.2, where you have a satellite who needs to visit these 5 different sites and then return back to Earth. And these numbers represent year amounts. So it's going to take 8.2 years to get from Earth to Mimas, 3.2 years to get from Earth to G here, etc. So if we were to use a brute force algorithm on this graph, there are 6 vertices, right? 6 different sites. So the number of routes we would have to check is 5 factorial. So remember that to just calculate the number of routes you have to check, you take the number of vertices, subtract 1, and then factorial that number. So 5 factorial is the number of routes we would have to check. 5 factorial is, it's more than 100. It's like 120 or something. So that's not something you want to do by hand. So instead what you do is you say, okay, fine. I'm not going to try to get the best path necessarily. I'm just trying to get a good route, and I want to get that good route quickly. So if we're going to start at Earth, it seems like a reasonable thing to do is go to Callisto, because that's the least cost path leading from Earth. Going to T is 8.1, to M is 8.2, G is 3.2, etc. So let's go to Callisto first. Now when we're at Callisto, notice that the cheapest edge from Callisto is back to Earth, right? That 1 point, sorry, I got confused by this 1.1. What I just said was not true. So we're at Callisto. Now we have 1.5 versus 3.1 versus 5.6 versus 5.2 versus 0.8. Okay, so just suppose for a second this 3.1 were the smallest. The only point I was going to make was you don't go back to Earth yet, right? So you never retrace your steps when you're doing this. So we've gone from E to C, and now we can't go back to E. So the cheapest thing we can do now is go to Io, which is 0.8 away. Okay, so we've gone from Earth to C to Io, and now from Io, we again have 5 options. We have this 0.8, we have a 1.1, a 3.6, a 5.1, and a 4.7. But we can't return to Earth yet, right, because we have to wait to return to Earth till the end. And of course, we can't go back to Callisto because we don't retrace our steps. So we go down here to G. That's the cheapest. Now from G, where should we go? Well, we only have 2 options left because we can't go back to E yet, can't go back to I, can't go back to C. Therefore, the only 2 options left are either Titan or M, and M is the cheapest option there. And once we're at M, we can't go back to Earth yet, so we must go to Titan, and from Titan we go back to Earth. So we get this path that I just described, from E to C, that was the cheapest, then to I, then down to G, then up to M, then over to T, and back to E. So this is the route that the nearest neighbor algorithm will give you. So notice that getting this route didn't take us very long. So once you get used to this algorithm, it takes you, I don't know, 25 seconds to do what I just did. But this route that we got is not guaranteed to be the best route. It certainly is possible that there's a lower cost route that the satellite could take. But the only way you could figure out what that other route is to do brute force, and that takes a long time. So here's another example. I didn't give this as a graph because it would be too big, but each of these letters represents a city. So there's city A, city B, city C, city D, etc. And let's just say for the sake of this example, these numbers represent mileage. So let's say that you are a political campaigner that needs to plan a campaign route, or maybe you're a band manager who has to plan a band tour route, you know, whatever context you want to give to this. But basically what we're going to do is we're going to use the nearest neighbor algorithm to find an optimal tour where home base is city B. Okay, so here we are at city B. We need to plan a route that visits all the other cities and then comes back to B. Well, notice to get from B to A costs 185 miles. Sorry, if you didn't know how to read this chart, that's how you read it. To go from B to A is 185 miles. From B to C is 121 miles. B to D is 150, etc. So if you're starting at B and you're going to use the nearest neighbor, you just go to the least cost option first. So you'll go from B to C. That's 121 miles. Now you're at city C. Where should you go? Well, you can't go back to B. Right? So this option here, this 121, that's off the table. But you can go to A. Notice A is cheaper than anybody else. Okay, now you're sitting at A. You can't go back to B or C. So your option, next best option is E. So you go from A to E. Okay, now you're at E. Well, you can't go back to A, B, or C. So where should you go? It looks like you have to go to D. Once you're at D, where should you go? Well, you can't go back to A, B, C, or E. Therefore, your next best option looks like it's J. Okay, etc. And so what you end up with is a path that looks like this. So again, this is pretty fast to implement if you know what you're doing. You just, wherever you're sitting, you can't repeat your steps until the very end, you know, until you finally close the loop back to B. So just look at all your possible options and choose the cheapest one to go to. So as one might guess, the repetitive nearest neighbor algorithm, right, its name is suggestive, is a variation of the nearest neighbor algorithm. So what we're going to do in the repetitive nearest neighbor algorithm is essentially just do nearest neighbor over and over again. And essentially what we're going to do is think about this picture here. When we did nearest neighbor, we were starting at Earth, right? That's where the satellite starts. And then we found a path that traversed through and went back to Earth, right? In repetitive nearest neighbor, what you do is you now construct the nearest neighbor path for all of the other 5 vertices. So we're just going to ask hypothetically, what if the satellite's base were on G? Let's find a nearest neighbor algorithm for it then. So starting at G, let's visit the other 5 and return to G. What if the satellite were based out of C? Okay, let's find a nearest neighbor algorithm route using C as a start point and end point, etc. We'll do the same thing for the other 3 vertices. So what the repetitive nearest neighbor algorithm says to do is it says to find nearest neighbor routes for all the vertices. So imagine starting at E, imagine starting at G, imagine starting at C, at I, at M, and at T. So if that sounds confusing, it's slightly confusing, but we'll walk through an example and it will be okay. So why would we want to do this? Why would we want to find nearest neighbor routes for all of the vertices? The reason is that the nearest neighbor tour depends on your choice of start vertex. If you change the start vertex, the nearest neighbor tour is likely to be different, and it might be better. So suppose back here, we did this starting at Earth, which is natural because that's where the satellite actually starts, right? But suppose instead we found a nearest neighbor starting at G. Would that help us at all? It seems like it wouldn't because, of course, the satellite doesn't start at G. But if you think about it, it actually would help us because suppose we start at G, and let's just say for the sake of argument, the path looks like this. So we just go right around the edge of this hexagon and back to G. You would say, well, that's not terribly helpful because I'm supposed to start at Earth. But notice that this hexagon that starts at G and then goes back around, you can think of that hexagon as starting wherever you feel like. This hexagon that goes around, you could think of C as the start point if you want to, and then just wind around that way. You can think of I as the start point if you want to, and just wind around. So in other words, once you find a path or a circuit, you can always just change the start point of that circuit. It won't change the actual path you're walking. So again, if G were our start point and we found this path to be the best from the nearest neighbor, we could just take this outer path and just consider E as the start point now and do the same path. So that's what the repetitive nearest neighbor algorithm says to do. It says, look, let's find nearest neighbor routes starting at each of these other 5 vertices. If one of those routes turns out to be better, like if starting at G turns out to be better, then we will just take that path and then consider it as starting at Earth. So that's what this is saying here. So changing the starting vertex gives you a different path, but that path will still go through Earth. It will still go through home base. So you can always just consider Earth as your start vertex if you want to. The path won't change. So since finding a nearest neighbor tour is an efficient process, it's not unreasonable to repeat the process several times, each time starting at a different vertex of the graph. In this way, we can obtain several different nearest neighbor paths, and then we can pick the best one from those. And once we've picked the best one from those, we can always just consider that path as starting at whichever vertex we feel like. So as we've just mentioned before, when you do this, oftentimes you get a path that starts somewhere other than where we'd really want it to start. So how do you deal with that problem? Well, as we just mentioned, remember that once we have a circuit, you can always start the circuit anywhere you feel like. So if you have a circuit, changing the start vertex doesn't change the actual path. So you can always just consider the circuit as starting or ending wherever you feel like. And then you can get a path starting at Earth if you want to. So let's do the repetitive nearest neighbor algorithm for this traveling salesman graph. So starting at A, he should go to C, and then from C, it looks like he should go to E, right? 120 is the least. So A to C, C to E. From E, he can't go back to A. His only choices are D or B. So it looks like he goes to D, and then from D, you must go to B, and from B back to A. So there's the nearest neighbor route for that. So this just shows that with arrows, right? A to C, C to E, E to D, D back to B, and B over to A. Okay, so oops, for some reason the cost is not showing up here. So let's do some cost on the fly here. So let's figure out what the cost of this is. So from A to C is 119. From C to E is 120. From E to D is 199. From D to B is 150. And then from B back to A is 185. So 773 is what it looks like the cost is. Oh my goodness. Okay, so 733 was the cost of this. Now, suppose we use B as the start vertex. So let's go back to the original picture and let's think of B as our start point, right, our home base. Finding the nearest neighbor starting at B, what does that look like? Well, we'd first go from B to C, because 121 is the cheapest. And then from C, where would we go? It looks like we would go to A, do that 119. So B, C, A, and then from A, we would go to E, and from E, where would we go? I've lost track. Okay, B, C, C, A, E, so E, D, and then D back to B. Yeah, okay, so let me just make sure I didn't mess that up. So starting at B, right, from B to C is the cheapest. From C to A is the cheapest. And from A to E is the cheapest. And now from here we have no choice. We have to go to D and then back over to B. Okay, so did I do that? Okay. Oh, sorry, this was the first one starting at A. Okay, here's the one starting at B. From B to C, C to A to E, E to D, and D back to B. That's what we said. Okay, so if you calculate the total cost of that, the cost is 722, which is cheaper, right? This is a cheaper path than this one. This is the original one we got starting at A. That was 733. Now, if we think of starting at B and we do B, C, C, A, blah, 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 right back to B, we get a cheaper path. Okay, but right now you're thinking, I don't want to start at B. I live in A. I want to start at A, right? Well, notice that when you have these arrows in place, the circuit in place, you can think of A as your start point if you want to. So just start at A. And then you'll go from A to E, E to D, D to B, B to C, and C back to A. So that's what I was saying earlier. Once you have a circuit just staring at you, you can always change the start point of that circuit and it won't change the underlying circuit. Right? The start point doesn't matter. You could start the circuit at D if you want to, and then you'd go D to B, B to C, C to A to E, E back to D. Okay, so the repetitive nearest neighbor algorithm says do this. So let's go back to the original graph. It says find the nearest neighbor root starting at A. We did that. Find the nearest neighbor root starting at B. We also did that. You also need to find the nearest neighbor path starting at C, D, and E. So you're going to end up with 5 different routes, all given by the nearest neighbor algorithm at separate starting points. From those 5 options, just choose the lowest cost one. And whichever one you choose, then remember that you were supposed to start at A. So whichever path you choose, now consider that path as starting at A. So we did B as a process. Okay, so the process is once again repeated using C, D, and E as the starting vertices. When the starting point is C, we get the nearest neighbor tour of this with total cost of 722. And that is still better than the original path we got, and it's just as good as the path we got starting at B. When the starting point is D, we get the nearest neighbor tour of this path, which also has a cost of 722. And when the starting point is E, we get this path, which gives us a cost of 741. Okay, so we got 3 paths that did all the best, right? We got this one from B, this, right, so B to C to A to E to D back to B, which we then considered as starting at A. So this path here is just as good. So if you want to consider this as starting at A, you would just say, okay, A to E, E to D, D to B, D to B, B to C, and then C to A. That's a relabeling of this, so it starts at A. And this one was also just as good, and this one was worse. So you can pick any of the 3 best ones and just relabel them so they start at A, and that's what the nearest neighbor algorithm will give you using the repetitive algorithm. So we'll just pick this one, it doesn't matter, with a cost of 722. This is the one that we got from starting a B, but then we just relabel it to start a A. And there you go. Here is a path that might or might not be the best path. We don't know. It very well might not be the best path, but it's still a good path, and we got it by doing 5 separate nearest neighbors and choosing the best of those. So here's a formal description of the nearest neighbor algorithm. Let x be any vertex, find the nearest neighbor tour with x as the starting vertex, and calculate the cost of this tour. Do the same thing for every other vertex in the graph. So if there are n vertices in the graph, you will get n different nearest neighbor routes. Of all of the nearest neighbor routes you obtained that way, choose the one with the least cost. If there's more than one, it doesn't matter. Just choose one of them with least cost. And if necessary, rewrite the tour so that it starts at the designated starting vertex. And that tour is the repetitive nearest neighbor tour. Okay, so that's how it works. So given a graph like this, if the homework or an exam just asks for nearest neighbor, then just start at your started vertex and just do nearest neighbor and you're done. If the problem wants repetitive nearest neighbor, then you have more work to do. But it's not a huge deal because if you can do nearest neighbor, then you can do it for other vertices, right? If you can do it at A, you can also do it at B, do it at C, D, and E. So you get 5 different paths. Choose one of lowest cost, and then relabel that path so that it starts at the guy's actual home base. Okay, so in conclusion here, these 2 algorithms are much more efficient than the brute force algorithm. It takes far less time to choose a path using either of these algorithms than it does using brute force, because brute force makes you list every possibility. Notice we didn't do that here. We didn't list every possible route. We just used some sort of like common sense rules to find a good route. So next time we'll finish the chapter, section 6.5. That's another efficient but not optimal algorithm called the cheapest link algorithm. It's kind of like nearest neighbor, but nearest neighbor is very like tunnel vision-y. When you're at a particular vertex, you only look at adjacent vertices and choose the cheapest. So when you're doing nearest neighbor algorithm, there's no global overview of things. So cheapest link it's an efficient algorithm with a more global view of things. You don't just consider your next move. You sort of consider the graph as a whole every time you make a move, and you sort of like cobble together a cheap path from doing that. So we're going to do one more algorithm to solve traveling salesman problems, and then we'll be done with the chapter.